In this class, what we're going to discuss is a few of the terms that we did not complete from Chapter 4, and also review some of those concepts. As you recall, the TB diagram, which is the temperature volume diagram, is shown in this figure, and you have several points that are very important here. You have this point here and this point here, and this refers to the saturation temperature, which you also call the boiling temperature. And at that temperature, you can either have liquid or gas, or a combination of the two. So whenever you're here and below, you have a compressed liquid. That's the term we use in thermodynamics. If you're at that temperature or higher, then you have vapor or superheated vapor. And in any range between these 2 points, what you will have is a combination of steam and liquid. There is a very important concept here, which is this pressure, and that is the pressure at which you have that saturation temperature. So if you have the saturation temperature that's related to the pressure, and if you have the saturation temperature or pressure, you have a temperature, and these two will be the same. And you saw that from the tables. Now what happens too is that this pressure is also called the vapor pressure, and we'll see that in a moment. So as you will recall, this TV diagrams, whenever you combine all of the different pressures, as the pressure increases, you will get this shape for your diagram, and this is your critical point. Above that critical point, you really cannot distinguish between what's liquid and what's gas. So you have the saturation or the saturated liquid, which is here, and the saturated vapor. So in the saturated liquid, of course, you will have all liquid, and in the saturated vapor, you'll have all vapor, but it happens at the same temperature and at the same pressure. If you are at points above the saturation temperature, so here is above that saturation temperature, then you have superheated vapor, and compared to saturated vapor, you can see here different properties, and just review those properties. This is taken exactly from the book, but basically you will have higher specific volumes, higher internal energies, higher enthalpies. So if you are at the compressed liquid, then you'll have something like this, and you look in different tables for this different properties. So you can find the internal energy. You can find, this is the enthalpy, which we'll define in a moment. These are just examples. And then we have the specific volumes. So the notation in this class is very important, as you can see. So if we have a saturated liquid vapor mixture, what we have is a ratio of the mass of vapor to the total mass of the mixture. So this definition is very important, and that has to be between 0 and 1. So if it's 0, that means that it's all liquid, because this is the mass of vapor divided by the total mass. And if it's 1, then you have all vapor, because then the total mass is vapor. So that's very important. Now, these are the equations you will need to solve the problems in order to calculate the specific volume of the mixture. Remember that whenever we had the graph of specific volume versus temperature, we have something like this. And if it's compressed liquid, well, you go directly to find the specific volume. And if it's also gas, you look for it. But if you are between saturated liquid and saturated vapor, what happens is that depending on the amount of heat or compressed liquid or compressed vapor is going to be the specific volume. So this expression is the first one you will need, how much mass of liquid and how much mass of vapor. Of course, this could be very complicated problems, but I just want to show you the basic problems that you might encounter as a civil engineer. And then this, remember that I'm using the bar to differentiate between what is velocity and what's volume. So this would be volume. So the total volume of the mixture would be the volume of the fluid or the liquid or compressed liquid, adding to that the volume of the gas. Okay, so this is very important. Then here you have the mixture, G for gas, then total. And we will work on example, I should go back here, example 4.4 on page 120. So remember to write down these equations so that we'll work on that problem in class. Now, one thing we haven't talked about, I only mentioned briefly at the beginning, was the ideal gases. And we're talking about steam. So steam can be treated as an ideal gas at low densities. So it would be low pressure and high temperatures. And the pressures, you know, whenever we say that how low is low, in our case it'd be below 10 kilopascals, then a gas behaves like an ideal gas. And an example of that is in air conditioning applications. However, in steam power plant applications, the pressures involved are very high. And even though they have high temperatures, the pressures are high. So in steam power plant applications, or whenever we're talking about steam machines, you cannot use the ideal gas law. Then you have to go and solve the problems using the tables. Remember the ideal gas equation of state relates pressure, volume, mass. This is the ideal gas constant, and temperature. This is the simplest and best known equation of state for substances. So remember, Pancho, vete y no regreses tarde. So you'll never forget that. The ideal gas law, the expression, that equation can take different forms depending on the ideal constant, gas constant that we use. Now, let me just show you this real quickly. If you have PV equals nRT, that means that N is PV divided by RT. So if you have gas from state 1 to state 2, the one thing that remains constant is the mass. So it would be P1, V1, T1, and then the mass in 2 has to be equal to the mass in 1, so it's P2, V2, R, T2. The R is the same, so whenever you're trying to solve problems that have to do with what's going to be the new volume or what's going to be the new pressure, then the relationship would be P1, V1 over T1 equals P2, V2 over T2, because these conditions, they have to be equal. So this expression you'll use for those types of problems that ask you about a gas in state 1 and then goes to state 2 under different conditions of pressure or volume, and then you have to calculate the temperature, or, you know, depending on what stays constant, constant pressure or constant volume or constant temperature, then you look for those variables. Okay, so then here we have, this is of course the volume, and remember lowercase is specific volume, which would be per mass. So if you multiply that specific volume times the mass, you get the volume, of course. So there's some manipulations that you can do to this main expression. And what normally we can do, and we do in thermal fluids, contrary to fluid mechanics and civil engineering, is that we use a modified ideal constant, RU, which would be a combination of the mass and the ideal gas law. So whenever we look at the expressions, then this is what we will have as the expression. So you'll see that the R now is different. So you need to be very careful what are the units for ideal gas constant, because that will tell you what is the expression that you will use. So if I have, for example, this expression here, kilojoules, then I have the, and also it will tell you what units you should use for the temperature, of course, for the mass, and then if you have pressure time volume, remember that that's unit of work, Newton meters or kilojoules, which this here combines that PV. Okay, so the pressure then has to be in pascals or kilopascals in this case, because you have the kilo here, and the volume has to be in cubic meters. So you have to look at everything, and in this class, that is very important. This is one of the group activities we'll do using the ideal gas law. So take a look at that expression. You have also copies of the slides, so you can review that. Now, I wanted to mention this because this is really neat. One of the concepts, that how we use this concept, is thermal fluids concept in civil engineering. Well, whenever we have low pressure or high pressure, it affects our system. In pipes and in areas near pumps, we can have some problem called cavitation. Cavitation means that there's bubbles forming in the liquid that we're pumping, and these are these cavities or bubbles form at low pressures on the suction side of the pump. Remember, the suction means that you have very low pressure, pressure lower than the atmospheric pressure. So what happens is that you will have cavities of bubbles that pass and form, and then they collapse when they go into higher pressure, and that causes noise, vibration, and damage to any of the components. It's really bad. It's almost like sandblasting your pump. So that will result in a loss of capacity. You cannot build the same pressure, and the pump's efficiency drops. Also, the pump will not last as long. So remember, those little bubbles, they form in the suction side, and when they collapse on the higher pressure side, then it's really, really bad, and also makes a lot of noise. It's like the pump is gurgling, and I will post some videos that show this gurgling noise of a pump whenever it's like, oh, it's really very typical noise that they will make. So I just want to introduce you to a concept. I'm hoping that you will learn some more in hydraulic engineering. But remember how we talked about the boiling temperature, and how the boiling temperature depends on the pressure. So higher pressure, higher boiling temperatures, lower pressures, lower boiling temperatures. So if we have a pressure that's well below the atmospheric pressure, you'll form bubbles. It's like it's as if the water boils. So that's what happens. In order to avoid this situation, the manufacturers will give you a requirement for pressure, or head requirement, at the suction side of the pump, and that is called the net positive suction head, and you have to make sure that your suction pressure is at least equal or larger than net positive suction head. Because remember that now, I don't know if you remember at the beginning I mentioned how that pressure, that saturation pressure, is also the vapor pressure. So that's a new concept. We're putting a new name to a concept that we already know. So that would be the vapor pressure. I hope that this helps. I will be posting more videos on Chapter 5. Email me if you have any questions. Thanks.